Okay, let's get started with today's class. Good evening, I'm Shankar. I'm your teaching assistant for this course, Fluid and Particle Mechanics, on offered on NPTEL by Professor Sumesh Thampi and Professor Basuraj. I'll be taking you through some of the questions that we are dealing with in the week 10 of the solved assignments and the solved and unsolved assignments, or the graded and non-graded assignments. So let's get started. Excuse me, 1 second. With that, let's get started with. Okay, yeah, yeah. So let's get started with the first question. These questions are based on uh, roughness, major losses, minor losses, etc. Those were the topics that were discussed in week 10 of the lectures. Let's start with the first question of the graded assignments. A liquid of density 700 kilogram per meter cube and dynamic viscosity 0.007 kilogram per meter second flows through a pipe made of cast iron. The pipe is 625 meters long and 100 millimeters in diameter. If the flow rate of the liquid through the pipe is given as 0.1 meter cube per second, then first question is we have to find the average velocity of the pipe in meters per second. So let's write down what we require for this. The average velocity of a pipe is flow rate divided by the area, and we know that the flow rate is given as 0.1 meter cube per second, and the diameter is 100 millimeters, which is 0.1 meters. So if we calculate the velocity, it will come to 0.1 divided by pi into 0.1 square by 4. I'll just give you 10 seconds to find out the answer quickly. Yeah, that's right. You'll get the answer as 12.73 in meters per second. So this is the average velocity just calculated directly from the flow rate and the geometry of the pipe. And yeah, for a turbulent flow, this answer is very much valid. Okay, let's move on to the next question, where it's given that and the Reynolds number characterizing the flow is what we need to find out. So, as we know, Reynolds number is rho v d by mu. The density is 700 kilograms per meter cube. The velocity we just found out to be was 12.73 meters per second. The diameter is 0.1 meter and the viscosity is given as 0.007 kilograms per meter cube. So all we need to do is substitute into the equation for Reynolds number. And we'll get this value as basically whatever value we found for velocity times 10,000. So it's 127300, indicating that this is a highly turbulent flow. Yeah. So let's move on to the next question, where the roughness ratio has been asked, and it is given that the material is cast iron. So if I go and excuse me, I was not able to download the I was not able to get the soft copy of the book that I have in my hand, and it is for finding out the roughness. The reference book is, you can use either Paris handbook or the one that was discussed in class was this book on which was on fluid mechanics by Frank M. White. And this is McGraw-Hill Publications. And in the 7th edition is what I have. So in this 7th edition, if you go to page number 381, you will find a set of you'll find a table which describes the roughness in pipes just after the Moody's chart has been described, and you will see that for a new cast iron, the roughness in millimeters will be equal to 0.26. So if you go to this page, you will be able to see the roughness will be 0.26. Therefore, the roughness ratio will be equal to 0.26 divided by 100. This is in millimeters. This will also will be in millimeters. Okay, the roughness ratio will be defined as the roughness to the diameter. Therefore, the roughness ratio will be equal to 0.0026. This will be not have any unit. Again, if you go to this particular book, this page number of this particular book, checking. Okay. Yeah. Sorry about that. Yeah. So if you go to this particular page number of 7th edition of Fluid Mechanics by Frank M. White of McGraw-Hill Publications, you can find the roughness ratio to be equal to 0.0026. Yeah. Okay. So we'll move on to the next question. We've been asked to calculate the friction factor over here. So there are two ways you can do this, either from Moody's chart. You can find out the friction factor. The other way is to solve the equation for the friction factor as follows: is minus 1.8 log 6.9 by Re plus epsilon by D by 3.7 power 1.11. This entire term will be in log. This is an explicit formula given by Haaland, and you can use either of these two methods to find out. So let me just take you through the Moody's chart, which I have copied it towards the end. Oh, apparently I have not added it here. It's okay, it's not a problem. So there are around 43 questions in this particular assignment, which makes it the longest assignment, but these questions are very easy. So let's just Google out the Moody's chart. Yeah, so there we have it. So let's me see if I can copy this image. So because we'll be using it multiple times in our I'm not sure how to. Yeah, there we go. We So there we have it. This is our Moody's chart. Yeah, there we have a much better version of it. Now that we have zoomed into it, we'll be able to take a look at what the values are. So we need to know what the relative roughness is and the Reynolds number is for to find out the friction factor on the y-axis. So we know that the relative roughness is equal to 0.0026 and the diameter is 100 millimeters. So let's take the sorry, the Reynolds number is 127,300. So 1.27 into 10 raised to 5. So let's go to the relative roughness, and a value of 0.0026 will be somewhere around this line. See, each 1, 2, 3, 4. So each of them is split into 0.0005 divisions. So this value will be 0.0025, this will be 0.003, this will be 0.0035, and this will be 0.004. Let's go to a value that's very close to 0.0026, which is 0.0025. So let's move along this line, and then it will slowly increase to such a value. And we know that Reynolds number of 1.27 into 10 raised to minus 5 will come and meet at somewhere around here. And at this point, if we extrapolate to the y-axis, we'll get a friction factor that is close to 0.025. Now, alternatively, this equation can also be solved using the Holland equation as shown here. And for that, we need to use some kind of equation solver. Oh, there is another equation that Holbrook and White have recommended. Maybe we'll use that equation. It is very similar except for the fact that there is no power here, and this second term is redefined as 2.151 by the square root of 2.51 by Reynolds number into the square root of the friction factor, and the coefficient before that is minus 2. So as you can see, this is an implicit function where you have a function of y in y, and this is known as transcendental equation. These equations can be solved to get the friction factor, and when you solve it, you will get the friction factor to be somewhere in between 0.02 to 0.03. I think I got the value as 0.021 something is what I got, 218 or something around that value is what I got. Please do check and confirm whether these values are consistent with the values that you got. If you have any doubts, please let me know. We finished the first question in first set of questions in that. Okay, let's move on to the next set of questions. And we have been asked to find out the head loss over here. So the head loss will be equal to F into L by D into V square by 2 G. Yeah, this is the head that we get from this. Yeah, so the F we got was around 0.0219025 times length is 625 by 0.1 times V square is 12.73 square in meter per second by 2 into 9.81 meter per second square. So I'll just give you a minute to finish off the calculations here. And we get the head loss as around 1290 meters. Again, please let me know if there is some mistake in any of the answers. I'll be happy to correct them. And yeah, this is the answer for this question. And we've been finally asked to find out the pressure drop across the pipe. So we found the pressure, the head loss to be 1290. So for the pressure drop is nothing but rho g into the HL. And here you have to use the fluid liquid that is being into the flow so that is 700 kilogram per meter cube times 9.81 meter per second square times the head loss, that is 1290. Which would come out to a value 8862267 in Pascal, which is 8862.27 kilopascal. Okay, there is a next question. There is a hydraulic diameter of channel shown in the figure that is given, and we have to find. We have to find the hydraulic diameter of the channel that is shown in figure. So it is given that the fluid comes in the YZ plane and leaves out through the YZ plane. So the area of this plane, that is the YZ plane, is being considered. Similarly, the fluid, since it is a wetting phenomena, fluid is wetted on these two faces and the faces opposite to each of these two faces. So there will be four faces, and that is the and the perimeter of that has to be considered. The perimeter of the flow direction, perimeter in the flow direction of this has to be considered. So let us first calculate the hydraulic radius, which is defined as the cross flow area divided by wetted perimeter. If this were heat transfer, we would have replaced this wetted perimeter with heated perimeter. And the answer will also change appropriately, because the heated perimeter need not necessarily be heated across the entire face. Only one face may also get heated up. So let's just look at this. The cross flow area would refer to the area that is occupied here, and where it is given that the fluid in the height here is equal to given by this 10 micrometer, and the width of the channel is given by 20 micrometer. So a simple area of a rectangle would be 10 times 20 times 20 divided by the wetted perimeter, refers to the entire face, the perimeter of the rectangle over there. So that would be 10 plus 20 times 2. And the hydraulic diameter is basically 4 times the hydraulic radius, so which is 4 times 10 times 20 by 60. Yeah. And this would give the answer as 13.33 micron. Okay, let's move on to question number 22, where it's given that while calculating the friction factor relationship for flow through an annulus with inner and outer cylinder radii being B and A respectively, four different students obtained the following relationship. They have given, okay, there's a small mistake in the question that's supposed to be there. There is no equal to sign here, which is hf times some value equal to f equal to equal to some value on the right side. So we shouldn't do any calculations to find out the answer. So in order to understand that, excuse me, so in order to understand that, what we have to in order to find out that, what we have to understand is, you know that hf is related to f as f times L by D times V square by 2G. And just a second, I'm just pulling out the equation um, for F. Okay, you will get the equation of F HF to be equal to 32 mu L by mu LV by rho G D square, and HF is also given by 32 mu times L times V by rho G D square. So all we need to do is rearrange and dimensionally analyze which best matches the value for the friction factor. So if we rearrange this, we can write this as HF into um, a characteristic diameter divided by the length times 2G by V square should be equal to F should be, and that again should be equal to 64 into mu by rho V. Let me just rewrite this D as capital D so that there is no confusion. Yeah, so rho V D, and this D refers to a characteristic diameter, and L refers to the length of this. So let's take a look at the cylinder like this, where it is given that the outer radius is A and the inner diameter is B, and the length of the cylinder we have to assume is some length L that is given over here. So let's now find out which of this is most accurately representing the value D over here. So let's take a look first at options, all the options. It is known that the viscosity should come on top and the density times the velocity should come on bottom. Therefore, automatically we can neglect these two students' answers because they have this is again a mistake in my part where I copied it wrong. Yeah, so you can see that mu rho v comes on numerator, so we can automatically neglect that. Then a dimension analysis of this and this needs to be done. So what you can see here is there is an effective length scale of L power 4. I'm sorry about that. There is an effective length scale of L power 4 that's coming out from this, whereas here this is L and this is L square, which will effectively give an effective power of L cube. Therefore, this is dimensionally correct with the analysis of characteristic length being 1 by L in the calculation of friction factor. But in the second case, you will see that it is the inverse of this. So you'll get L on the numerator, which means that mu L by rho V will come on. This, in fact, will give you mu by rho V L, which is in fact the Reynolds number coming up. And this will not be able to give that. Therefore, the correct answer is given by student 1. I understand this is a lot, this may be a little bit confusing, especially with a lot of mistakes in the questions. But if you have any doubts, I'll just wait for a minute so that you can understand. Okay, let's move on to the next question. They have asked for the expression for the hydraulic diameter, and as we had mentioned earlier, the hydraulic radius needs to be counted out, which is the cross flow area by wetted perimeter. And in an annulus, if you think about an annulus as like this, where the inner is B and the outer radius is A, the cross flow area is the area between these two, and the area that is calculated, and that area is calculated by just subtracting the area of the larger one minus the smaller one, and this will be the A and B are the diameters, so we have a 4 factor of 4 that's coming up, and the wetted perimeter is basically the perimeter over here plus the perimeter over here. So it's the sum of the perimeters of the inner and the outer outer radius or outer circles. Now we'll be getting this as a square minus b square by 4 times a plus b, and this is the hydraulic radius. So hydraulic diameter is 4 times the hydraulic radius, which is a square minus b square by a plus b, and this will come out to a plus b times a minus b divided by a plus b, which will in fact be equal to a minus b. Now I think there is some mistake in the question here as well, because the correct answer is just a minus b, and the answer that best matches our result is 2 times a minus b. So I think we have to go for that answer as whatever we see. And the loss coefficient that describes the measured minor loss is and in the lectures that is discussed, we and the Professor Sumesh described all about the head loss, the velocity head, and the loss coefficient. And this loss coefficient is basically perfectly or correctly defined as the head loss to the velocity head. Okay, next are a set of true or false questions. We'll do them one by one, and it's very straightforward. There's nothing much to think about here. So let's get started with the first question. So minor losses will always be smaller than friction or major losses due to long pipe. Not necessarily we can have a partial closing or a partial opening, which may in fact result in the minor losses being more than the major losses. It's called minor losses because in the majority of the cases it is smaller, generally smaller, but that doesn't mean it is always smaller than the major loss. So this answer is false. Moody's chart can be used to calculate minor losses in a piping system. That is again false because Moody's chart is used to find out the friction factor, and the friction factor is used to calculate the major losses in the system. So Moody's chart cannot accurately cannot predict or cannot calculate the minor losses in the piping system. Moving on, question number 3. The friction losses associated with the partially closed valve is considered as minor losses. This answer is correct because the property of the valve is considered, or how the gate closure of the valve is considered, and therefore it still counts as and the loss due to a valves, fittings, elbows, joints, etc. comes under minor losses. So this statement is true. Next, in a sudden contraction, flow separation in a downstream causes the mainstream to contract through a minimum diameter called the vena contracta. So this statement, as discussed in class, when there is a sudden expansion in the flow, sudden contraction in the flow, what happens is the point of minimum flow separation does not happen at the place where the sudden contraction has happened. It will move on to quite a distance after that. Excuse me, and just redraw this. If there's a sudden contraction, the point of minimum separation will be happening at a point that is after the flow has or after the separation has occurred at this point basically, and this is called as the vena contracta. So this statement is true. Now fifth question number 15. The loss coefficient of all submerged exits no matter how well rounded is unity. This is true, and yeah, this is just a statement that should be known. That's basically straightforward. In question number 16, the vena contracta exists whenever the piping system has a sudden expansion or a sudden contraction. And yeah, that statement is not entirely correct. It is false. It happens when there is sudden contraction, but sudden expansion is not necessarily the truth. Okay, question number 17. The pressure drop in a 500 millimeter diameter horizontal pipe is 100 kilopascal, sorry, 10 raised to 5 in SI units over a length of 50 meters. We just have to find the shear stress at the pipe wall. And we know that the pressure drop is actually given by F times rho V square by in times L by D, whereas the shear stress is just equal to F times rho V square by 2. So when we do this calculation, we'll get the shear stress and the pressure relation as minus delta P by L times D by 2, which will come out to minus 100 by, sorry, it's not 100, or you have to just do it in kilopascal. So this is in 100 kilopascal by 50 meters times d by 2, which is 0.025, sorry, 0.25 in millimeters, in meters. It's just 250 millimeters by 2. And you'll get this as 0.25 kilopascal. And this is the shear stress at the pipe wall. So I'll just give you a minute to catch up on whatever true or false questions we have done and this last problem that we have been doing, and continue after in a minute. Okay, let's move on to the next set of questions. Where the first part is water, that is density of 1000 kilogram per meter cube, viscosity of 1 centipoise, flows through a pipe at 900 centimeter cube per second, as shown in this figure. The water pipe has 2.5 centimeter diameter and it slopes upwards at an angle of 30 degrees. The inner surface of the pipe is fully rough, that it gives a constant friction factor of 0.024. The flanged globe valve is fully open, with the mercury, which density of 13,550, viscosity of 1.56 into 10 raised to minus 3 Pascal second. Manometer shows a 10 centimeter deflection as shown here in the image. The length of the pipe across which the pressure drop is calculated by the mercury manometer. So basically you have to find the length of this pipe, which is just from geometry can easily be done. We know that this distance is 3 meter. So if we consider this distance to be 3 meter with an inclination of 30 degrees, we'll be able to find out this length L. And this is nothing but uh, yeah, 3 divided by cosine of the angle between that. And this will be nothing but 2 times root 3, which is 3 point approximately equal to 3.48 or 3.46 in meters. Next, what is the average velocity of the fluid in the pipe in meters per second? We know that just the simple formula that we've been using all the time. The flow rate is 900 centimeter cube per second. The water pipe is centimeter, 2.5 centimeters. So the velocity will be equal to Q by A, which is 900 into 10 raised to minus 6 meters per second divided by pi into 0.025 in meters square by 4. Which will give the velocity to be equal to 1.83 in meters per second. Next, we have to find out what the pipe head loss is. So, pipe head loss includes the change in pressure head and the gravity head. And the gravity head is just basically the vertical distance between these two. And that can be found out by equating it to the tangent or tan value of the angle over here, which is tan 30, should be equal to opposite by adjacent. So let's call that hz divided by 3. So hz is equal to 3 times tan 30. And tan 30 is basically 3 times tan 30 is basically 1 by square root 3, which will give the answer of square root 3, which is 1.73 meters. Yeah, and similarly, the pressure head, let's call that as H. L will be equal to F times L by D times V square by 2G, which is 0.024 times L refers to the overall length, which we calculated here to be equal to 3.46 times the diameter will come here, which is 0.025. times V square is 1.83 square by 2 times 9.81. Which will give the value of 0.56. Okay, there is one more calculation that needs to be done for calculating the pressure difference. This is delta P by rho G, and delta P is given by, this is the rho water, which is the fluid that is flowing through the pipe, and this is the mercury times D times H is this height that is given in the manometer. Let's just call that as the height Lm divided by rho W times G. So this would be 13,550 times 0.1 by 1000, which is 1.355 in meters. So the pipe head loss will be equal to the change in the pressure head plus the gravity head, and this is the gravity head and this is the pressure head. Therefore, change in the pipe head loss will be equal to 1.355 plus 1.73, which is equal to 2.18 meters. Sorry, 3.18 meters. Excuse me. Three 3.08 meters. Yeah, that's much better. Next, we have to find out the loss coefficient, which is the total head loss to the velocity head. So the loss coefficient is called that as K, is the total head loss, which is H as we defined earlier by HV, and this will be 3.08 by 0.56, which would come around to somewhere between 5 point something. This would be 5.5. let's move on to the next set of questions. Consider the given figure given. There are 125 feet of 2-inch pipes, 75 feet of 6-inch pipe, and 150 feet of 3-inch pipe, all of cast iron. There are three 90-degree elbows and an open globe well, all flanged. If the exit elevation is 0 and the operating fluid is at a volumetric flow rate of 0.16 feet cube per second at 20 degrees Celsius. The roughness height for cast iron, I think I forgot to mention the unit, it has to be in feet. And if we go to, as mentioned earlier, the book on page 381 of the book on fluid mechanics by Frank White, you'll find the epsilon value to be equal to just get the value out for you. Yeah, it is 0.00085 in feet, and this value in millimeter is what we wrote earlier as 0.26 millimeter. Now we have to find out the roughness ratio in the 2-inch pipe, and that is equal to 0.0008 divided by, this is in feet, 2 inches has to be converted to feet, which is 2 upon 12 feet. Which will come out to be equal to 0.0048. Next, we'll have to find the roughness ratio in the 3-inch pipe, which is again same formula we have to use, which is 0.0008 by 3 by 12. And I'll get this value as 0.0032. And again, this exercise remains the same about calculating the roughness ratio, which is 0.0008 by 6 by 12, which is 0.016. Next, you have to calculate the flow rate through the 2-inch pipe, and it is given that the flow rate in the starting on the exit is 0.16 feet cube per second. Therefore, the flow rate doesn't change throughout anywhere throughout the pipe. Only the velocity and the area will change. Therefore, the flow rate through the 2-inch pipe should be equal to 0.16 feet cube per second. Extremely sorry, this is feet cube per second. Next, we have to find the average velocity, which we have been doing till now, which is Q by A. And this will be equal to 0.16 feet cube per second divided by pi into pi times 2 by 12 in feet square times or divided by 4. Which is equal to 7.33 in meters per second. Next, we've been asked to calculate the Reynolds number for the flow, which is rho v d by mu, and it is given that the operating fluid is water. So rho is 1000 in kilograms per meter cube. The velocity in feet per second. Okay, I think we just need to find out the density of water in pound per feet cube. So let me just Google that out, or let me just find out the correct conversion. Yeah, it is 62.43 pounds per feet cube. And the velocity we found earlier was 7.33 meters per second. And the diameter is 2 by 12 feet. Oh, sorry, this is not in meters per second. Terribly sorry. This is in feet per second here as well. And the viscosity is, let me just again convert that to it will be 0.0067 in sorry, this is pounds per feet second. So you can just calculate the Reynolds number based on this formula, which is 62.43 pounds per feet cube times 7.33 feet per second times 2 by 12 feet divided by 0.0067 pounds per feet second. Oh, sorry, this is not 0.0067, this is 0.00067. There's another 0 here. So we'll get the value as 113.834, somewhere around that. Okay, let's find out the friction factor in the second 2-inch pipe. So we have to go back to our Moody's chart and find out what the value over there. So I'll bring the Moody's chart here. Yeah. Let's go back to question number 29. Yeah, there we are. Okay, I'm just figuring out how to add the page here. Yeah, there we have it. So we have a roughness factor that we have described to be around 0.01, sorry, 0.0048, and the Reynolds number is 1.13 into 10 raised to 5. So 0.004 would correspond to here. Maybe this line would be the most accurate line. So a region between these two is where it would be. And it would meet 1.13 somewhere here. And if we extend that, we'll get a friction factor of somewhere around 0.02 to 0.03. Okay, so we can write the friction factor F to be equal to 0.025. Okay, let's move on to question number 30, where we have to do the floors. Repeat the same experiments for the flow rate, for the average velocity, for the Reynolds number, for the friction factor, and for the friction factor, for the 6-inch and the 3-inch pipe. And finally, we just have to find the loss coefficient over here at the 2-inch entrance. Yeah, these are very straightforward questions, and finally you have to find the turbine head, where you have to add all the heads together, and that will be equal to the turbine head, and its work will be equal to the power will be equal to the head times rho g times the velocity. Yeah, that's what you'll get as the turbine here. The power turbine power here. And after that, it's very straightforward. I'm leaving these calculations to you. If you have any doubts, please let me know. And yeah, and we have the practice problems. This is very similar to what we've been doing till now, where we have a liquid of density and kind of viscosity given, pipe dimensions are given, which is when the average velocity, Reynolds number, roughness ratio, friction factor, and the head loss. So with this, I'll stop for this week's problems. If you have any questions, please do let me know. um, Sorry. Yeah, please do let me know if you have any further questions. With that, I thank you for your time and attention.